Let's now look at how sketching functions can help us find points of intersection. So to start with, I've got two functions and I'm going to want to sketch them on the same diagram, so let's do a quick roots analysis. So the roots for the first function are going to be at x equals 0 and at x equals 1, and the roots for the second function are going to be, well, I've got a repeated root there at 0 and the other root is going to be at x is 3. The first function, two roots, so quadratic. The second function has three roots, so it's going to be cubic. It's negative cubic, so it's going to take this form, and it's got that repeated root there at 0, so I know that's where the local minimum is going to be. Now let's draw these onto the same graph. So what do I have? Well, starting with the cubic is going to look something like this, turning point and then off. So we've got this here as the point 3. The quadratic goes through at 0 as well, and also goes through at the point 1. Now the quadratic graph in the long term is not going to take as larger values as the cubic graph, because let's say if I take 10 squared it's 100, and if I take 10 cubed it's 1000, so its entry in towards 0 will be less steep than the cubic graph, as will its exit. So there I have my graph, and I've got these 1, 2, 3 points of intersection. From my sketch I know that I'm going to be able to find three solutions from this, so I then set my equations equal to each other. So I've got x lots of x minus 1 is equal to x squared lots of 3 minus x. If I expand this, that gives me x squared minus x is going to be equal to 3x squared minus x cubed. Rearranging would give me x cubed minus 2x squared minus x is equal to 0. Factorizing tells me that x lots of x squared minus 2x minus 1 is equal to 0. So I can find one of my solutions, which we already knew about, which was going to be the point where x is equal to 0. The other two solutions are going to come from solving x squared minus 2x minus 1 equals 0, which we can do by completing the square. So that becomes x minus 1 all squared minus 1 minus the other 1 equals 0, so x minus 1 all squared equals 2, so x is equal to 1 plus or minus the square root of 2. Now I want to find the points of intersection, so I need to find the associated y values, and to do that I'm going to use this quadratic equation to substitute in the values. So when x is 0, well, that's nice and straightforward. Y is 0. Now in here I've got wrapped up two solutions together. One of those solutions is x is equal to 1 minus root 2. So the y value there would be 1 minus root 2 lots of 1 minus root 2 minus 1. Well, if I multiply that out, then the 1's there are going to cancel, and I'm going to have negative root 2 times negative root 2, which gives me positive 2, minus 1 lot of root 2. In the other case, I'm going to have the x value that is going to be 1 plus the square root of 2, and then to find the associated y value I've then got 1 plus the square root of 2, lots of 1 minus, plus the square root of 2 minus 1. Again, these cancel, and expanding here I'm going to have 2 plus the square root of 2. In the final example, we're going to look at how these two graphs look and then use it to solve some related equation afterwards. The first graph is reciprocal. It's a reciprocal x squared graph, so I know it's going to look something like this. The second graph is cubic. It's positive cubic, and it's got a repeated root at 0, so that local maximum there is going to be at 0, and then I can use that information to draw my functions. So I've got the cubic function that's got a repeated root there at 0, and will look like this, where the other intersection point here is at 5, and then the other graph is 5 over x squared, which will look like so. Now from this, what can we see? Well, I can see that there's only going to be one point of intersection. So for the second part, state with reasons the number of solutions that this equation has. Well, it obviously must be related to the first part, and let's see how. So 5 over x squared, let's imagine these two things you can equate. Well, we know we can, because we've found a single point of intersection, and we should have something that looks like this. Now if I multiply across by x squared, I get x to the power of 4, lots of x minus 5, and then if I subtract the 5, I've got 0 is equal to x to the power of 4, lots of x minus 5 minus 5, which is the exact same equation that I've got there. So by equating these two functions, I get this equation that needs solving. Well, it doesn't actually need solving because all it's asking me to do is to state the number of real solutions that this problem has. Now I can see quite clearly from these graphs that there is only ever going to be that one point of intersection, and that's the point that I would make. So state with reason the number of real solutions of this function. This function has one real solution as functions have one point of intersection. And that's it. I'm complete.